Let's do a few examples translating English sentences into quantified logical symbols and back. Let's start with the sentence, I have a whiteboard. We're going to turn this into logical symbols. So whenever you have this kind of translation problem, you're going to turn an English sentence into logical symbols. You always have to do two things. We have to, actually, let me go over here and make a little principle for this. One, define your set or possibly sets. And two, define your predicates. So you are not ready to go stringing any fancy symbols together until you have defined your sets and defined your predicates. So let's go ahead and define sets and predicates that are going to work for this translation. I'm going to define W, the set of all whiteboards. And I'm going to define a predicate H of X, H of X. I have whatever X is. So H of this specific pencil means I have this specific pencil. Okay, so now I'm not saying that I have any specific whiteboard. I'm saying that I have a whiteboard. Could be any whiteboard. Another way to say this, and this is another helpful trick for when we're working with logical translation problems, is to try to translate this into language that sounds a little bit more like the language of there exists and for all. So when I say I have a whiteboard, I'm not saying any specific whiteboard. I'm just saying one of the whiteboards in the world, I have one of them. Or there exists one which I have. So I'm going to translate this. There exists a whiteboard which I have. This now tells me what to do pretty clearly. I have my sets, I have my predicates, I have a translation. I've just rephrased the sentence in such a way that sounds a little bit more like a quantified logical statement. I can write now, there exists an element X in the set of all whiteboards such that I have it, such that I have X. There exists X in W such that H of X. And that's my complete logical translation for this statement. I define a set, I define a predicate, and then I, after some rephrasing, am ready to turn that entire statement into a sequence of logical symbols. Let's do another one. Everyone is a math person. I believe this deeply. Everyone is a math person. How are we going to do this? Well, steps 1 and 2, we have to define our sets and we have to define our predicates. So I'm going to define the set P, the set of all people, and I'm going to define a predicate, M of X. X is a math person. So now if I need to, I can do some rephrasing, but I think actually this one we can just jump right into in order to express as a logical proposition. I'm saying everyone, so that sounds a little bit like for all. So I'm going to start writing for all X in P, so that's every element of the set of people, or another way to say that is every person. Every element of the set of people makes this predicate true. For all X in the set of people, M of X is true. For all X in the set of people, X is a math person. Or this is a pretty roundabout way to say that every person is a math person. So translating from English sentences into quantifiers, it's not necessarily always this straightforward, but you always, always, always want to start by defining your sets and defining your predicates. Now let's go ahead and try to translate a sentence that, as we'll see, is going to involve multiple logical quantifiers at the same time. So here's our sentence. Every person is loved by someone. Every person is loved by someone. So if we start breaking this down a little bit, we see, okay, well, every person here, that kind of seems like a for all kind of idea. But then someone, not any specific person, and not necessarily every person, someone, not sure who, that sounds more like a there exists kind of statement. So in order to translate this sentence into logical symbols, we're actually going to need both for all and there exists. And of course, we have to define our sets and our predicates. So let's go ahead and start doing that. It looks like this is a statement about people. Let's say human beings. That's fine. So I'm going to say here, okay, P is the set of all people. And I'm going to define a predicate. And because I have a complicated sentence here, that it's going to involve entities. Two entities. So when I say two entities, there's the person who is loved and the person who is doing the loving. So in order to express this, I'm going to do something we haven't seen yet, which is to define a predicate that actually has two arguments. X loves Y. X loves Y. So, for example, with this predicate, L, put an example over here, L of Phil and math is true. Phil loves math. Okay, so now what we're going to do is we're going to try to express this sentence, every person is loved by someone, in logical quantifiers. And to do that, we're going to use this two-symbol logical predicate as well as our quantifiers for all and there exists. Let's start by translating the phrase every person. So every person, we have done this before. This is for all X in the set P of people. That's every person. I'll put my comma here. For all X in the set P, so for every person, there is someone who loves them, or there exists somebody who loves them. There exists an element Y also in the set P, such that now we have to be a little bit careful about our order with our two-symbol predicate. Remember that we're looking for someone who loves the person we're looking at, so I actually need Y to be the person who is loving X, which means L of Y and X is what I'm going for. So if I wrote this out in English, for every person, there exists some person who loves them. Okay, so we can get more and more complicated logical expressions just by defining more sets if we need to, defining more complicated predicates that might accept multiple inputs, and then using multiple logical quantifiers in order to express our ideas. Now, one thing that it's important to notice here is that the order really matters. So I had a for all, and then I had a there exists. And that order is really, really important. So suppose that I made a mistake here, and instead of doing my for all first, I actually did my there exists first. There exists y in the set of people P, such that for all x in P, L of y and x. So this proposition looks kind of the same. It has all of the same symbols. They're just in a different order. But the order matters a lot because this proposition says something really different. This says there exists a person who loves every person. Or another way to say this is somebody loves everybody. So this is a very different statement, and indeed, these statements are arguably have different truth values. So in my first statement here, every person is loved by someone. I hope that all people can have in their lives someone who loves them. So this statement I hope very much to be true. This statement, somebody loves everybody, is very different because what that says is that there's one person in the world who loves all 8 billion other people in the world. I don't think there's anybody in the world who knows all 8 billion people in the world, let alone loves them. So this statement, this incorrect translation where we swapped the order, that statement is definitely false. This is a false statement that would have been true if we'd gotten the order correct. So when we're working with multiple quantifiers, one thing that you really have to pay attention to is writing them in the correct order. One of the reasons we care so much about quantifiers is that they help us define mathematical ideas very precisely. So it's fun to be able to translate English sentences into quantified logical expressions, don't get me wrong, but that's not really the point. The point of quantified logical expressions is to be extremely precise about how we define technical concepts in areas like mathematics and also computer science. So consider the following kind of scenario. So this is a scenario that comes up when we're thinking about things like routing. You're trying to figure out the best way to drive somewhere or walk somewhere. I have 2 points, A and B, and there's lots of different ways that I could get from A to B. Here's a few of them that I've drawn. And then I'm going to draw one suggestively in a different color. So lots of ways to get from A to B. And often in computer science, for example, we would like to find the best way to get from A to B, and often best means shortest. So how do we find the shortest route from A to B? This is a complicated algorithmic problem that you'll study in future classes. But before we get to the problem of how do we find the shortest path, let's actually think about something a little bit simpler. How do we define the shortest path? How do you define what it means for something to have the shortest path? We kind of intuitively understand this from our sort of built-in understanding of how the world works. But a built-in understanding of how the world works doesn't do you much good when it's time to write some code or to write a proof. You need to be able to express your idea symbolically. So let's go ahead and start doing this, and let's see if we can figure out our challenge. Challenge here. Define what it means for a path to be the shortest path in a set. So when I say in a set, I do mean that because we can label all of these paths here. So here's path A, path B, path C, and path D. And this is a set of possible paths. And what I want to do is I want to define what it means formally that path B is the shortest path in that set. So how are we going to translate this? Here's our sentence to translate. Path B is the shortest path in the set of paths. And let's give this set of paths a name. I'll call it P. So P is going to be the set path A, path B, path C, and path D. Okay, so in order to craft this definition, what we're going to do is we are going to define a predicate here. So our predicate is going to be a 2-input predicate again. So I'll call it L, different L from last time, L of X and Y. And L of X and Y means that the distance of path X is less than or equal to the distance of path Y. If we gave symbols to the distance, so for example, if we decided that the distance of path X would be written d sub little x, d sub little y, we could also say that L of X and Y is a statement about the inequality d of little x is less than or equal to d of little y. So now I have a set defined and I have a predicate. And so I am ready to rock. To say that path B is the shortest path in the set of paths, that is equivalent to saying that if I look at all the other paths, for all possible paths in the set P, it is the case that B has a distance that is no longer than that path I'm comparing to. Or, if I want to write it out in full math and skip the formal predicate, I can do that too. For all x in P, the distance of B is less than or equal to the distance of x. So this is, and indeed in math we would probably most commonly go with this kind of expression. So this is an expression of the idea of shortest path, or more generally, minimum of a set. And what I want to highlight here is that using these quantified logical operators, I can define this fully symbolically in a way that I could then prove things about, or possibly even feed into an automated proving program. And it'll even tell me things about how to code this up. If I look at this, I can almost see, kind of in here for all x and p, well, that looks like a for loop. And then here I'm going to need to use some less than or equal to comparisons. So this symbolic representation also helps me understand something about what I should do in order to implement my idea.